for a viscoelastic material, how the material properties are used in FEA tool if sinusoidal load is applied on the component or assembly. So for this, here the question was, so the person is asking what material properties are used in the FEA tool if sinusoidal load is applied on component or assembly. In FEA softwares, there are probably 3 ways by which you can input the material properties. One would be the hyperelastic material module, in which you input the stress strain graphs of different tests like uniaxial tension, planar shear, volumetric compressions, and so on and so forth. Apart from this, you have 2 alternate inputs for viscoelastic data. For viscoelastic data, you can carry out your stress relaxation and your creep experiments, and there is something known as Prony series by which you can import that data. Apart from this, the third is the frequency related tabular tables that are available in softwares like Abacus Standard, by which you can import the loss modulus, the storage modulus, and the tan data. All the 3 can be input into the FEA softwares. Okay, in Abacus, the way it works is you first of all define hyperelastic, then go to viscoelastic, then the frequency tabulated input module. In ANSYS also and LS-DYNA also, or MSc Mark also, the same input procedure is there, but it's just a matter of trying to find out, where the click is there, where it is located. So apart from that, your sinusoidal load can be applied as a frequency related property, and the result you will get is a frequency related output, and your simulation can be carried out for frequency analysis. Okay, so that was my question, answer for question number 1. Storage modulus is only to be used for oscillating loads. By oscillating loads, I mean, you might be meaning the cyclic loads. Yes. When you carry out a viscoelastic deformation for time domain, there is no storage modulus or loss modulus that is output. The storage modulus, the loss modulus, and a tan delta is a property which is output from a frequency test or from a cyclic test. Okay, so these are the only properties that are available from the cyclic test. So that is why you can input that as a cyclic load only. So that would be my answer for question number 3. What are the general conditions for testing tan delta for a tyre PCR compound and O-rings? Time, temperature, strain rate, and frequency. At the top, so here the answer will be everything depends upon the field service conditions of your material and component. Say for example, you have an engine mount, or you say for example, let us go to your PCR compound. You have a PCR compound, and most of the time, when you have a passenger car radial, when you have a passenger car that is running on a road on a speed of say from 0 to 110 kilometers per hour, the maximum frequency ratings for such for such a condition are 0 to 15 hertz. Okay, because the way the suspension is designed. Now, say for example, if you have a sports car like a Toyota Supra or a Lamborghini or whatever, then the suspension is designed to be stiff. Okay, so your suspension components or your tires or your different, the ride quality providing components, they see a maximum of 0 to 40 hertz. So from 15 hertz, 40 hertz. Okay, so those are the general parameters. Now, for example, say you talk about an O-ring, but O-ring doesn't see any dynamic loops. What O-ring will see is a temperature. So it depends. Now, if the O-ring is applied as an under the hood component in India, sure, room temperature to 150 degrees C. If it works somewhere in Mongolia or somewhere in North America, then you will go from minus 20 degrees C or minus 40 degrees C to 150 degrees C. Okay, so everything depends upon what is the field of application of your material and component. But the broad way you should look at it is first comes the application, comes the service conditions, and from those service conditions, you, based upon your engineering judgment, you define the test parameters. Same for O-rings, it's an under the hood component, so you're mostly, it's going to be in a static condition its whole life. The force is going to decay, the material is going to set, and that's how leaks would happen. So that is what you would characterize the material for. Okay, so that's how it is. So that would be my answer for question number 4. What could be failure limit for viscoelastic material? Is it same total strain possessed by a material before failure or something else? The question is for both static and dynamic loading conditions. See, when you carry out the test on a static material or a tensile test on a quasi-static process. Say, for example, your material fails at 10 megapascal at 1000% strain, right? So now, if you apply machine design principles, you know, the undergrad class book, Shigley, machine design, you will know that for steel material, your endurance limit is 0.554 of your yield or your failure. But here you don't have any such conditions or any such theories for rubber material or for a polymer material. So based upon your engineering judgment, based upon how the material component behaves in its service conditions, you will say 40% of, instead of 554, I will take 0.40, 0.35 or 0.60. Okay. Now, again, that would be for a static condition. But when you go for a dynamic condition, a material or a component has always to apply or satisfy some sort of stiffness conditions. So you will sort of do your experimental testing for that. In the first test, you do it, you know, on a fresh component. You do a fatigue test and you do a static test and you find the stiffness. Then you do a long range fatigue test for a viscoelastic test or a fatigue test, endurance durability test. You find out the stiffness again, right? So in the first case, before the aging, before the endurance, say for example, your material handles 500 Newton at 2 millimeters. You run it for some time, then you do a stiffness test and again, it deforms only 300 Newton, it deforms 2 millimeters, but the load is only 300 Newton. Now, based upon your service conditions, you have to make a judgment, 500 Newton and it decreases to 300 Newton. Whether this stiffness is good enough or not. Generally, a decrease in stiffness of 20% or more is not good. So that would be considered a failure. So this is how you demarcate both the conditions and you come up with your failure criteria. That would be my answer for question number 7. Any idea testing the polymer material with pre-stretch? For static conditions, we normally do not have any pre-stretch. But when you carry out a dynamic test, always there, the pre-stretch is always applied on the compound. When you do a cyclic test, you have to apply a pre-compression on the part and then you apply an amplitude. So your polymer material under dynamic test is never under zero stretch. It's always pre-stretched to some amount. And that is how it is. So that would be my answer for question number 8. Which are the tests required to access the degradation properties of a biodegradable polymer which will be used for vascular applications? Normally for vascular applications and for biomedical applications, most of the test protocols are dictated by a regulatory authority, whether it be FDA or whether it would be the DGFT in India. So if coming from a subject matter viewpoint, material degrades under temperature, material degrades under frequency. So these are the two parameters under which your material would see degradation. But to go into a little bit more grainy detail, you would have to consider the FDA regulations. How do you test the protocol? What is the frequency of application? What is the temperature of the test? So for that, you have to consider all those things, the regulatory authority documents. So I would not be able to, give a very detailed answer to this, but broad range, your material degrades under temperature, frequency applications, and long-term, loads. So these are the three broad areas. Once you want to go into the grainier details, please consult the regulatory authority documents. So that would be my answer for this. We would like to conduct FEA for a biodegradable vascular stent. I would like to know which are the material properties required for FEA inputs. Please consider that the device will be biodegraded in 2 to 3 years. I don't know whether this would be the right, we can take this offline, and if you can send me an email with the required, details, I can get back to you. This would be probably, this has to be done at a more private level. But overall, if you want to conduct an FEA, as discussed in the class, you go through the different material characterization protocols, you generate your material constants, and you import those into the FEA. This is the broad inputs that you would require. To go into grainier details, would require a little bit more study of your end use of what the regulatory authority wants as an output, and based upon that, you would have to develop your test protocol. So that would be my answer for this question. How a data from simple tensile stress strain data can be used during FEA simulation for UHM to predict the performance? For a UHM-WP material to predict the performance of component, and the UHM-WP material should be considered as elastoplastic or viscoelastic or hyperelastic during FEA analysis. This question has more to do with the FEA analysis, so it would be better if we can stretch it offline. But see, at the outset, it will be your judgment call. It will be the engineer's judgment call of how the material has to be modeled. And that judgment call will come from his understanding of what the outputs are and what he wants to simulate. Okay, so a simple tensile stress strain data is not going to give you all that, sophistication of a complex material model, which a viscoelastic material is, and which a hyperelastic material is, and which an elastoplastic material is. So I do not know how to answer this question in more details, because certainly the FEA engineer would need to, would need to go through his set of required outputs and make a judgment call on that. So an outsider would not be able to successfully answer this question. So that is my answer for this question. How the data from simple stress strain curve data can be converted to various material model available in FEA software. All this information is there in the the software manual, whether it be Abacus, whether it be LS-DYNA, and whether it be ANSYS. So how you take the stress strain data and how you convert it to a material model is all there in the FEA software manual. You will have to go through the manual and figure it out. So is there any software that can be used to convert the stress strain data from simple test to? Yeah, all the Abacus has, ANSYS has. I don't know whether LS-DYNA has, but certainly Abacus and ANSYS have. So to compare the influence of processing additives at different pHR level on tan delta on rubber roller application. What kind of test conditions are advisable to adopt for testing? I am little bit, this would go outside of my, domain of competency or domain of expertise. I am not an expert on compounding or, processing. So this is little bit outside my domain of expertise. So. How we can do material characterization for a polymeric tube that of 3 mm outside diameter and 300 micron normally used for manufacturing of stent in order to use the material for properties during FEA to predict the part performance. This is more of a specialized nature, and this question needs to be studied and probably answered outside the scope. This would not be probably something that I can answer at the top of my head. So I would have to refer, and this communication has to be done in private.
Okay, Karthik, that's all the questions we have. Thank you very much for addressing it appropriately. And guys, some of the questions you need a private discussions, or you may write to the Karthik. Okay.
Yeah.
Karthik, thank you very much.